Okay, so with that, let's launch into part one. Now, I need to explain this first before I go any further. This thing called the BAER. So what you see here, BAER, is the burn area emergency response, BAER. And the burn area emergency response physically is a report. All right. What happens here, at least in the US, is that when there is a fire, there is a burn area emergency response, a bear team that comes in during the fire. Sometimes the bear team comes in late in close to the fire. What the bear team is doing is the bear team do not engage directly in the firefighting, but the bear team have a very important role to play. The bear team will assess the extent and the severity of the fire, and then the bear team will assess the risks associated with the fire. So for example, oh, sorry, I saw something from Everett. Oh, Everett.
Hey. Yeah, I just wanted to interject. Once you're done talking here, I just wanted to talk a little bit more about what goes into the bear process.
Okay. In fact, once I finish this slide, I would invite Everett actually to comment, because the rest of this talk is on knowledge graph. Yeah. So the bear team plays a very important role. The bear team conducts a risk assessment of the likely after effects of the fire, for example, landslides or heavy erosion leading to a landslide, and possibly polluting water sources that eventually might result in a debris flow, which has in the past been shown to be extremely damaging and very, very risky. And so the rest of the demo is based on a hypothetical situation where the contents of the bear report, all right, the bear report is actually submitted up through the chain to, for example, Forest Service headquarters, USDA Forest Service headquarters, to request for emergency funds to, for example, create mitigation measures so that you lessen the risk of landslides, for example, right? So this bear report is extremely important. It has a funding, it is a funding request, but the funding request really is to prevent loss of life. And so the bear team has, I think, 10 days from the time that a fire is contained to submit a report up the chain to request for funds. And so this is what the knowledge graph that we will build is based on. And what you will see in the next few slides is a hypothetical, I would like to say a hypothetical depiction of a knowledge graph that represents a bear report. And I'd like to invite actually Everett Hinckley to provide comments. So Everett, if you remember, those of us who joined us for the ESIP summer meeting, Everett was one of the speakers from the USDA Forest Service. And Everett works, he leads the remote sensing team within the USDA Forest Service. Everett?
Yeah, thanks, Brian. And one thing I wanted to mention is that one thing that is sort of wedged in there before people go out into the field to do the bear work, there's a process called there's a BARC map, which is a burned area reflectance classification map, and that is produced, and it sort of infers burn intensity. So you look at a Landsat image before the fire, and you look at one after the fire, and you do an NDVI classification on the two maps to see what the change is, and the reflectance classification infers burn severity, but then the bear team takes those maps out to the field with them to validate those maps. And the reason that's done is they want to have a general understanding of the bear process is there to guide rehabilitation efforts in the field immediately after a fire is put out, so that you can do minimize things like downslope wasting and other impacts to the ecosystem there. So the BARC map is one of the things that they take to the field with them as they're going out to assess the burn severity.
And this is not a prearranged signal for me for Everett to say this, because later in the slides, Everett, you'll be pleased to know that I have a reference to the BARC process. very briefly, and also the process by which you just mentioned, where you have ground truths actually going out to do a ground truth of the actual burn severity. That's also incorporated in one of the figures data. So I will point that out in a few slides.
Okay, as usual, we're thinking along the same wavelengths here. So
exactly. Okay, so with the bear report, this is what I'm going to show you next. Oh, okay. This is not for you to digest, but this is the poster that was exhibited at the ESA meeting, and I'm going to dive into the lower right-hand side here of the poster, where it shows you a mock-up graph of the bear report. Okay, so don't attempt to read the whole poster now. Okay, so this is the mock-up of the knowledge graph in that poster. A little bit complicated. We're not going to talk about the whole graph. Instead, we are going to just talk about this part of the graph, and later we're going to actually only attempt to replicate this left-hand side of the graph because we don't have much time. Okay, so just let me explain very quickly how to read this graph, right? Now, so graphs are meant largely to reflect, quote unquote, the natural way of thinking about things, because the human brain, of course, is neuronal. The human brain is associative by nature, right? For example, the Rorschach test, where the ink blot test, the psychologist will show you an ink blot test, and the question to you would be what comes to your mind as you look at the ink blot test, right? And so the mind works by association. Graphs really utilize that same principle. It is an associative mapping mechanism where, for example, here we're talking about a fire. So for a given fire, right, a fire has a geographical extent. So you can represent that information using a geographical extent idea, right? A concept. I shall use the term concept from now onwards. So the concept fire always has some kind of a geography, and what you would like to do is to be able to describe that geography. In this case, for example, the geography of the fire is within the USDA Forest Service district Canyon Lake. So the Forest Service maintains a bunch of controlled names for forest districts, and this one happens to be Canyon Lakes. And here's an identifier for that particular forest. Now, and in this case, this geography of this Canyon Lakes district has a geography overlap, meaning that if you were to look at it, if you were to pull out, like in a GIS manner, the shape of this ranger district, you may be able to see if your GIS is configured appropriately, if you have the correct data layers. You may see that this Canyon Lakes Ranger District has an overlap with State Highway 14, and this is actually a civil infrastructure. This thing here called civil infrastructure, which is a vulnerability in a fire. And so, what we have done here using a graph is we have encoded that knowledge of a fire with a geography, and the geography covering a piece of the land which has State Highway 14, which is a vulnerability that somebody should be worried about. And of course, the somebody is anybody who's fighting in the fire, or civilians hoping to escape from the fire, because State Highway 14 could be an evacuation route, right? And so that in that way, if you read the graph down this way, the fire also has a BAER, has a bear report. And like I said, bear reports bear reports are funding requests for like emergency stabilization. I have a typo here, unfortunately. With an estimated cost of 30.2 million. So the bear team is going to put forth a request to Forest Service. I need $30 million to shore up the slopes, for example, to prevent debris flow. That's what the bear report, that's what is encoded here. And within the bear report, you will see a bear report typically has it has many sections. At least the ones in Colorado, we have seen that they have definite sections which are actually consistent across bear reports. One of the sections we'll talk about watershed condition. For this watershed that the burn area is happening in, this is the kind of water repellent soil that we are expecting. So for those of you who have attended earlier ACC Ag and Climate calls, you will see that we had a previous talk where we talked about hydrophobic soils forming as a result of fire. And so when you get water repellent soil, it means hydrophobic soils, that's dangerous because the soil is not able to absorb water. And so you're having a situation where the water, any rainstorms after the fire is going to result in water running off steep slopes, which is bad, all right? And so you encode, there's one way of encoding that information in this way. And the whole purpose of doing it in this way is, for those of you who are familiar with the relational databases, you might ask, couldn't I encode this information in a relational database? Yes, the answer is yes. The issue is that, the drawback with relational databases is that documentation wise, so I used to program a lot, and I'm very strict about documenting my code, because I know that if I look at my code 2 weeks later, as most of you who have coded will attest to, you look at your code in 2 weeks later and you have no idea what you just did 2 weeks ago. The same thing with database structures. When you have when you're working with relational databases, and I used to work with relational databases, these things called relationships has geography overlap, has bare, has watershed condition. It is not explicit in a relational database. Yes, you can record and you can actually write down in a documentation, this relational table is linked to another relational table using these keys, and the implicit relationship has watershed condition. However, that documentation, it relies on you to maintain the documentation. In a graph database, on the other hand, you have to explicitly say what is the relationship between a bare report and this thing called a watershed condition. Is it a chapter? Is it a section in the report? Right? You have to be as explicit as you can, and this documentation of relationship is preserved with the database. So that is the advantage of a graph database. So having said that, you need to learn some of the terminologies associated with a graph database, and this is what we're going to next in the next 4 slides. Okay, so these things are called nodes, N-O-D-E-S. These things here that my cursor is hovering over, right? Fire, geography, vulnerability. These are all called nodes. Now, the nodes have labels. One important qualifier I've got to say. What you see here, the terminology I'm using, nodes, labels, and so on and so forth, this is a terminology that the graph database called Neo4j uses. So Neo4j is a commercial database. They have free evaluation versions, but this is very specific to this database called Neo4j. Other databases have their own terminology, but the concepts, there's an overlap in concepts. They're not identical, but there's an overlap, right? So these labels are what you call nodes. So for example, if there is a person node in this graph database, I don't have a person node. The label for the person node could be Forest Service Ranger, could be a label. The other label could be Forest Service employee, right? And in Neo4j, each node can have one or more labels. You have to have, I think you have to have at least one label, but you can have multiple labels. For example, here in the stabilization treatment, meaning that under the watershed conditions section, the Forest Service, the Bear folks would say that, okay, because we have so much water repellent soil, we are recommending these stabilization treatments. So for these nodes that capture information about stabilization treatments, you will assign the label stabilization treatment, but you can assign another label for the road trail treatment. So how are you modifying the road condition to stabilize the roads? That's one way to read this. And land treatment. So in this case, for example, if you are dropping mulch onto the slopes to absorb some of the runoff water, that is a land treatment. So the knowledge engineer might say, this is a stabilization treatment as one label. The other label, which I, the knowledge engineer, choose to label this node is a land treatment. So you can have multiple labels per node. Okay, next, relationships, extremely important. This is what actually drives and what powers the whole database through relationships. And the last thing I want to say is the very other important thing is in graph databases and in well, not true in general, but in Neo4j, for each node, you can have properties like these: the burn area, how many thousands of acres, what is the volume of the sediment that is potentially going to wash off the slopes. Again, these are properties of nodes. The strange and wonderful thing in Neo4j is that the relationships can have properties also, and I'll show you an example later. Okay, now, so I'm going to switch to real-time demo right now using arrows.app. This is the lower left-hand side of the graph that you just saw. So we're going to draw this out in arrows.app. And I'm going to just stop my screen share for a quick second so that I can switch screens to arrows.app, and my screen share is about to restart. Share a screen to this one. Okay, so I hope you see my empty screen now. Do you see my empty screen, Bill? Do you see?
Yes.
Good. Okay. So what you see here is arrows.app, and yeah, the URL, you key in arrows.app, and it brings you to an interface that looks like this. Now, you normally start off blank like this, right? And so if you hover your arrow here, you can do new, right? New graph, store it in either Google Drive or web browser storage. Web browser storage is a local store, so it stores on your local drive. And Google Drive, you can store in Google Drive. Right now, I have it stored in Google Drive. Okay, so let's create our first node. All right, this is a node, and let me bring up. Hang on, if you excuse me, I need to refer to my other slide. Okay, the first node that I'm going to create that you saw in the poster is fire, right? So here's my node. I'm going to assign it. Remember a label called fire. So okay, and there you go. This is my fire node. Now I can choose to assign it properties. So what I'll do here is I hover. Oh, by the way, if you're asking what is this caption thing up here on the screen, I would advise you to ignore the caption. Arrows.app was recently adopted by Neo4j, and so they brought over this thing called caption, which I don't find really handy. So ignore caption, concentrate on just labels and properties. So under the properties, the fire, for example, if you remember earlier in the graph, I have something called fire name, and I'm going to say valley part. So there you have it. This is the property, and the value of the property is fire part, right? Okay, I'm going to add another property called fire number. So this is a fire ID, and fire number, I'm going to give it a property of the property value of Colorado LFC G999. Now there are other properties that you see in the example. I'm not going to waste your time going through all the properties, except to say that what you have here, I'm going to quickly choose a theme. A theme allows you to pick a layout to visualize the graph. So I'm going to just choose a theme. There's this chunky theme, which I think is the default. I normally go for the browser theme, based on Neo4j browser. Don't worry about it. Once you experiment around with it, you see why I choose this theme. It's beginning to just look a little bit like what you saw in the poster, where you have the label fire, the properties, fire name with the value part, the property fire number with the value Colorado LFC G999. Now, so this is a node, and as you remember from the example, I think by the way, I don't think you guys can see. I think better zoom in. One note, I'm going very fast here because I'm running out of time. One note about the interface is that this interface is a little bit clunky, as in to zoom in, if you have a mouse with a scroll wheel, you can press Control on your keyboard and use the scroll wheel to zoom in like this. I discovered very late that you can also use your trackpad to zoom in and out. In fact, and to scroll horizontally, you use your trackpad. So for those of you who have trackpad, if you are comfortable with trackpads, I would recommend that you use a trackpad. The mouse, this interface doesn't work too well with mice. Anyway, so I'm going to create a linking node, right? So I've got a fire node. I'm going to create the bear node. Now to do that, I would put my cursor near the edge of the node. And once you see the node being highlighted, you can click and drag out an arrow. And here you get it. So this is the bear node. So I'm going to say the label here is BAER, right? And as you can see here, the arrows tool automatically suggests to you that there are other labels that it knows about fire node because I previously created the fire label. So this is a nice way if you are expanding out your graph and you have multiple fire nodes so that you don't create again a slightly differently labeled node, right? So this is the way that the tool reminds you there's already a fire node. You can use that if you want, but if you insist that this is a new label, fine. And I'm going to insist that this is a new label. Now, so for the bear node, I'm going to add in just two properties. Again, the same thing. The tool will say, look, you have other properties that you defined prior to this. You have the fire name property and you have the fire number property. Nope, those are not what I want. I want a new property called report type, which is, this is the funding request, right? And if I hit enter here, I can very quickly fill out a bunch of information. Suppression cost is 30.2 million. All right. And again, you can just enter and so on and so forth. But let's stop here. Oh, darn it. So here you go. So we have two nodes. Let me zoom out. It gets tricky. This gets very tricky. Well, okay, we have two nodes connected already, and we want to give it the relationship has bear, right? And so, well, sorry, hang on. I would click on this relationship, and then I can type in has BAER. Here you go, has bear. So there already you have your first graph. I'm just going to create one more node and one more relationship. Then I'm going to show you a strange and weird property of Neo4j. So I'm going to create a link from a bear report to a watershed condition. Remember earlier I showed you something called watershed condition. Okay, and again you can place as many properties as you want, but I'm going to create two additional nodes and I'm going to stop there. Stabilization treatment. All right, I'm going to say I want the label, the properties. Hang on. Stabilization treatment. All right, and then there. Then this one is the relationship is has stabilization. There's a typo here. Treatment, and again, I can create another one and so on, which again, the label of the prop of the relationship is has, there's an error in the code actually. Anyway, this is just to give an example of how you can create your graph. And this one is a special case, for example, where I will show you this relationship has bear. You can actually add a property to this. So the property could be status of the report. Whoops, there's a typo here. Status, and it's a draft. It's in draft instead of completed. Okay, and let me add in just one more property, one more relationship to has watershed condition. Okay, so effectively we have created our graph, and let me just show you one more thing, and I'll open up for questions. So you can you can actually work in this the graph in groups. And the important thing about this is to download, export. Go explore this by yourself, but there are a number of options. So when I click download, export, it allows you to, of course, download as a PNG or a graphic. SVG is a vector graphic, so you can import it into a vector graphic package. Cypher, this is important because if you decide eventually to play around with Neo4j and you get the free trial version, which is actually extremely operational. The free trial version, this is the command, the query language called Cypher, C-Y-P-H-E-R here. This is the Cypher query language which you can copy and paste into Neo4j to create this knowledge graph in a Neo4j, right? And this the JSON representation is also useful. So, for example, if you guys were to work in a group, all right, to collaborate on a knowledge graph, we don't exactly know how to do this yet. We've only experimented with this for 2 weeks, but one possibility is to, of course, share your arrows.app graph on Google Drive, and then you allow your collaborators to open that arrows.app graph using Google Drive. I think there are some issues with it. We have yet to fully experiment. The other way of doing it is to export it to JSON, like push it up to GitHub, because GitHub will easily ingest a JSON file. And so your collaborators can pull down the JSON file, edit it, and then push it back up to GitHub. So that's one way of collaborating in teams. Again, there are ways to use this for collaboration. We have yet to experiment with it fully, but I think I better stop here because I am running out of time. So questions? Is this so overwhelming? I hope not.
So at the end of this process, does this build your database in Neo4j?
Yes, you can. In fact, once you export it, in fact, actually you can even import this JSON into Neo4j to create the actual database, or you can use this. And yes, it's a direct import into Neo4j, which is why it's nice that for our activities leading up to January, that's what Bill and I have been thinking, that we can distribute this work in small teams. The small teams can work individually to create parts of the graph in subgraphs. And then later, I will need to reconcile all the little subgraphs and use these import facilities to import it into Neo4j. But yep, it's a direct, it can be very easily changed, converted into an actual graph database, very easily.
So Brian, because the sharing function via Google Drive is, there's still issues, right? Still not working. So it could be that going forward up to the January meeting, the work that we do, however, whatever the size of the group, we will have to work kind of around that inability to share directly. So we talked about a little bit, so there are workaround of how to do that. So it'll just be a little less convenient.
Martha has an interesting question. It's actually a tough question. So Martha asks, are arrows always one way? Oh, Martha, go ahead. But I need
I was just saying hi.
It's a very good question.
Yeah.
It's a very good question because it's actually laden with a lot of things. So the answer is the arrows in Neo4j are they are enforced in one-way arrows. Okay. You can create an equivalent. You can create an arrow. You can create a relationship going back in the opposite direction. It is counted as a separate relationship. You can even use the same label, the same hash stabilization treatment, but in the other direction. But for reasons that I said it is not recommended. The weird thing in Neo4j is when you create your graph, Neo4j conceptually and practically, it will force you to choose a direction one way. But the very strange thing about Neo4j and graph mathematics is that when you pose a query to the database, so that's a nice thing here. You can tell the database, look, I'm interested in this stabilization treatment where I drop mulch onto the lands, onto the slopes, and you can tell the database, I'm interested in this fire. This fire, when they dealt with this fire, did they ever drop mulch after the fire was contained? So you can ask the database this, and regardless of which direction any point the arrows point to, as long as there is a link between the fire and the stabilization treatment, the database will be able to tell you, yes, there is a linkage between the stabilization treatment and the fire, regardless of how many intermediate paths. So I could have a pathway like this. I could have some other ridiculous, this is the direct pathway, that's not fun. But you could have arrows that go from this back to here. The database can go wild. You can specify to the database that I do not care about the direction of the arrows. Just find me how fires and stabilization treatments relate. So that's a nice thing about a database. I mean, well, this kind of database.
Okay, thanks. Very helpful. Good information.
So for the CMS, the carbon management folks, and anybody else who's interested in this, when Bill and I we started this whole thing about from data to decisions, right? If, for example, from the agency's perspective, if you need to justify why your data product has it done any good for the world, right? This is why we wanted something like a graph database. You can lay your hands on, say, one report, right? So here you have a bear report, but you can lay your hands on one report, like a journal publication is considered a report. So for this journal publications, you ask the database, show me how is this journal publication related to this particular funding item in the FY 2022 funding, FY 2022 budget request that requested monies for this kind of data products. And so regardless of how messy the database gets, if you structure your knowledge in the appropriate manner, and if you ask it in the right manner, I'm not saying that you need to ask the database nicely. I mean, between humans, you need to ask nicely, but you can be really cruel to the database. The database can be really, really convoluted, but the database manager, the query manager will find you a pathway between very distant nodes, as long as there is a path. Of course, again, out of scope of this discussion, but you can ask things like, the database is gonna chunk away for like 40 seconds and return me the results. That might be true, which is why then you need to think about how you optimize the database. But again, that's not, that can be done. It's a matter of time. So we ran way over time for this section. It is interesting stuff, but so if you're interested in continuing with us on this, we hope to use a process like this for over the next 3 months, and that's the next part of the next part of the talk meeting agenda. I mean, what do you think, Bill? Should we go on to the next part of the talk?
Yeah, I think so. We have about 15 minutes. So
okay. Sorry. So guys, I know some of you are probably bursting with questions, but I need to move on. So I'm going to quickly share the oh boy, I'm going to share my screen again. And for efficiency, I'm not going to go full screen. I'm just going to put this like this. Okay, so part 2. Again, for the rest of the year, again, this vision, some of you have seen this multiple times. The vision that Bill and I have been trying to push for the last few months, and where we're going to continue to push for the next few months, is interoperability of data and information. It's important that we're talking about data and information across fire management phases. Fire management phases being prediction, pre-fire mitigation planning, during fire, blah, 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 blah. All right. So in order to do that, what we've been doing is looking at, we held that workshop in the ESIP summer meeting, but we also looked at the Moore Foundation's Fire Immediate Response System workshop report. This report was released after a workshop in 2019, and Everett Hinckley from the Forest Service was an attendee, and Jenny Biggs from the Moore Foundation, who's still on the call. Jenny headed up the report and organized the workshop. And so what Bill and I did was we looked at the report, and we found that what we were trying to do in the ESIP summary meeting was very similar to what the Moore Foundation had already done in terms of sketching out blue skies scenarios. And so these are the two scenarios that Bill and I had chosen from within the report. The two scenarios are expanded and strategically placed networks of automated ground-based data collection cameras and sensors for fire detection, and so on and so forth. Real-time 3D hourly forecasts of fire behavior and fire spread, right? Taking inputs from authoritative platform and including up-to-date information on fuels and wind conditions. And so what you see here is you're talking a lot about data fusion and data integration from multiple data sources that may be used for routine monitoring before the fire, and it also could be used, that data could be extremely useful in the immediate aftermath of a fire, or actually during the actual fire. And so it fit our requirement of looking at the framework of interoperability between fire management phases. But here, at least for the next half year, we're not going to focus as much on information interoperability. I think we're going to talk about just data interoperability. The information interoperability aspect is a little bit harder because it gets into quite a bit of natural language processing and AI. And we figured just let us stick with the data end of things, because with the data end of things, there's a lot of ESIP expertise on data management, given that, you know, the bunch of folks sitting around here and outside of this cluster, we know quite a bit about how do you make metadata discoverable, and like even things like how do you use ontologies to make that metadata discoverable, regardless of how the person who's looking for the information may describe what he or she is looking for. Anyway, there's a lot of data management that's implicit in this, and so Bill and I thought we would focus on sensor data fusion and integration, and how do you repurpose that data for different fire management phases. And as a reminder from the ESIP 2021 summer meeting, and this gets to what Everett had talked about. There were 3 takeaway points. What I have here on the screen are 2 of the 3 takeaway points. But takeaway point 2 was better integrate fire behavior model data, values at risk data, and sensor data. Again, we're going back to data management and data integration. And this is where Everett had talked about burn area reflectance classification, and how do you use in situ and remote data to better estimate burn severity. So again, this was takeaway point number 3 from the workshop 2 months ago, right? So with all these, with the Moore Foundation report, those 2 bullet points, and these are the 2 bullet points, what we have arrived at is this diagram here, which I'm going to try to zoom in just a little bit. Okay, I hope you see it here. Hang on. Okay, I think you can see it. Okay, so what you have on the left-hand side here is we intend to use a use case, right? From San Francisco that was highlighted in the Moore Foundation report. I have not explicitly mentioned it, the use case here. The use case is based in the San Francisco Bay Area. So if you're looking at on a map, you know, across the right from the bay, that area called the Moraga. Oh boy, Bill, I don't remember the name of the fire district.
The Moraga and Orinda.
Yes, Moraga Orinda Fire District.
Fire district, yes.
That area. Now, so what the Moore Foundation has funded is a small prototype project, right? involving UC Berkeley also, to have in situ sensors that will trigger a satellite imagery acquisition by a planet, one of the platforms on the planet satellites. So if this is for detection of fire ignition as close as possible to the time of detection of a potential fire. So the sensors on the ground are integrated in the way of triggering satellite acquisition. And so that's an example of multi-sensor data integration. But what we wanted to do is also to ask the question, granted that you have that data which is being measured when there's no fire, but can that data be used for other purposes? For example, can you use that data that is used for fire ignition? Presumably there's a use case to use that same data to inform the condition of wildfire fuel. Now, wildfire fuel, how dry the fuel is, how dry your vegetation is a function of things like the amount of humidity in the atmosphere. Now, so if those sensors in the San Francisco Bay Area, if they are already measuring atmospheric moisture in order to trigger a planet satellite acquisition, Bill and I have been thinking, well, it would be nice to reuse that data for a fire fuel modeling algorithm, like an ongoing algorithm that is constantly ingesting real-time data to assess the status of wildfire fuel real time. Okay, so that's the use case that we are thinking of experimenting with. Bill and I have yet to have the final discussion with a very progressive fire chief by the name of David Winnecker in the Bay Area. Once we confirm this, we intend to use that as a way to instantiate, to start creating a knowledge graph. All right. So the knowledge graph will start with functional requirements. Again, I'm borrowing a lot of NASA terminology here. This is, for those of you who are used to doing this, this is essentially a trace down. This is a traceability matrix for those of you who are used to looking at these things and gathering functional requirements and tracing that down to technical requirements. This is in effect, we're trying to create a traceability matrix, but in the form of a knowledge graph. So what we intend to do is, there are some functional requirements that stakeholders like Fire Chief David Winnecker has stated. We will progressively break these requirements down into very short statements that satisfy this condition of that sounds like a requirement. A requirement is normally phrased as a statement that has the word shall have or shall be. So anyway, that's functional requirements and requirements engineering. We will capture this requirements in the knowledge graph, but link it to information about how those sensors have to be physically deployed over the landscape. Again, that prototype project funded by the Moore Foundation has already done this. So it'll be a great way to actually link, to capture the knowledge that project has already implemented, capture into a knowledge graph to help us model the knowledge graph. And once you have some idea of how the sensors are physically implemented, then we talk about the data, right? The data from the sensors. How can they be captured? What are the best practices that we as folks have learned through the years? How should we be managing the data so that that data is discoverable for other purposes? And speaking of care, fair and care, so the fair and care requirements can be imposed inside the database as a requirement also. It could be a requirement such that the data that is collected by the distributed sensors is fair compliant. And if you are using data, for example, that overlaps with tribal jurisdictions, then you need to be careful about additional requirements. And so here is the care bit of the thing, the care part of the requirement. And so we can try to implement this as a knowledge graph. Again, the whole idea is traceability. Now, this is the use case, right? This is the use case that we use to instantiate this knowledge graph. But during the meeting in January, what we want to do is to bring the other use cases that were in the More Foundation report and also from our workshop 2 months ago, right? What we want to do is to bring those requirements, use the knowledge graph as we have it in January. It's not going to be a completed knowledge graph. It's not going to be refined, but we're going to use that knowledge graph to say, look, for these other requirements, these other use cases that we know of, the objective during January, the meeting in January, is to create a narrative, right? It's a one pager, or it could be 2 slides with bullet points. We really don't care. But the objective is to have workshop participants and those of you who choose to join us in January to come up with the narratives, again, PowerPoints or a one pager that points back to the knowledge graph to say, look, for the case of, like, for Everett, we said mentioned the thing about burn area reflectance classification, BARC, right? One of your teams may say, you may write a one pager to say, in order to implement a new capability that satisfies Everett's requirements, from the knowledge graph, this is how we can reuse data and how we can ingest data from these sources and implement it in a way such that it can be used during pre-fire mitigation planning and also used during the after-fire mitigation processes. Again, so that's the objective of the kind of big idea about where we're going. Did I miss anything, Bill? I know we're running out of time.
Oh, just to add one thing. So in addition to the narratives, there are bound to be some gaps in the knowledge, well, in the whole process that we also want to capture via the knowledge graph.
And so very quickly, if I want to hear some feedback in the time that we have left, but what we will do for October, November, December is to hear from a number of stakeholders and folks from the ESIP EnviroSensing cluster who have some experience in the physical implementation and some of the data management aspects. So again, we're going to build this knowledge graph over the next 3 months through the series of monthly meetings. So that's what we're after. Is that a good idea, bad idea, too much to handle? We hope to hear from you guys now.
Well, Brian and Bill, I think you guys are on the right track here. So let's just keep pushing forward with this.
Okay. Martha is expressing her vote for the idea.
I think it's a really good idea. There are lots and lots of things to consider, including in a knowledge graph. And yeah, I'm enthused.
Yeah, because one of the things that actually I'm kind of interested in, I mean, if you're looking for it from the ecological standpoint, right?
I am.
Of course, there are a lot of variables that control soil moisture and vegetative evapotranspiration. That is actually part of the graph, which I don't have it explicitly in here. But if you look at my screen, I think I'm still sharing. Yeah, if you look at my screen, near the point where you're talking about data, you're talking about variables. And by the way, there's a cute thing which we're going to experiment with, which is using variables in ontologies, right? So some of you have heard about ontologies, but we're going to actually, in this knowledge graph, we're going to document all the way down to variables. Now, those variables connect up again to science concepts like evapotranspiration and soil moisture. What are the various controls and impacts of environmental variables on soil moisture and evapotranspiration, for example. And so, yeah, there's a capability here also to build in a science aspect. And for those really gung-ho, if you can think of actually implementing a full mathematical model as a knowledge graph and chuck it in here, but that's I think a bit too ambitious. Just saying.
Thanks.
Just to add one more thing about the process in creating this knowledge graph. So Brian and I are still talking about how best to engage everybody to help fill out the knowledge graph as we move towards the January meeting. So we'll be back with everyone once we figure that out.
Joseph.
Hey.
Joseph.
Hi, everyone. This is fantastic. Joseph Bell from the USGS and also the EnviroSensing cluster. I may have missed a key component early, and I'm going to try and use what's on the screen now to ask my question. So these concept graphs, these knowledge maps, they're not a skin for an existing database. They're more like a map, like a map to how one might get the data. So for example, say a functional requirement is that a sensor has to publish data to an internet page, right? So then in like the physical implementation, you would get the name of the sensor, the manufacturer of the sensor, maybe the sensor's range of observations and variability. Could you then also have that link to the real-time data there? Or are those connectivity links to actual data and maybe the reports from the previous example, are they typically absent from this? I guess what I'm struggling to relate my question to a database. And so is this a skin for an existing database, or is this a means to map out the information where you might be able to get it?
So unfortunately, the answer is both. I mean, as in it can be a skin, but it also it can also actually hold the actual data, which is kind of horrible. But so let me give you the skin example first, right? In the skin example, what we intend to do minimally for a skin example is if you trace it down to a data source, you should one of the properties within one of the nodes in the database should be a DOI. The DOI should resolve to some persistent landing page for that data product. Right, and this is common nowadays. So from that respect, for the skin argument, that's where the skin stops. The skin stops at a DOI that is resolvable to a landing page at the repository's data product page. Well, for that data product in that repository. So on the other hand, and here's where the horrible thing comes in. It is conceivable if you have a database like storing real data, like in a relational database, like just like megabytes of even you think about a relational database with just 3 fields, but like 20,000-30,000 rows, you can, and people have ingested these kinds of databases into the graph database. The issue there, of course, is that if you update your relational database out there, then you need to synchronize your updates out there with your graph database, and it gets kind of messy and horrible. And so for the most part, what you want to do is to think about the graph database mainly probably as a skin in the skin model. But of course, on top of the database, you would have an application layer. I mean, it could be as simple as a Python script, because the Python scripts and R and lots of other languages, well, not lots of other languages. It depends on the support that Neo4j gives you, for example. But Neo4j will support Python. So if you use the skin example, yeah, you put your DOIs and your URLs and URIs in the database, right? But in your Python script, you will pick up the URI from the database through a Neo4j call through Python. And then it's up to your application then to connect to a to connect to a relational database, or use some other APIs that are provided by those databases to grab data. So yeah, it's all possible depending on which way you do it.
Thank you. You really hit on the part, that kind of static or not, the potential to create a non-unique example where you could go to one database, and then if another one hasn't updated, you would then have kind of laggard values persistent. Thank you. This is fantastic.
Awesome.
I'm excited. Yeah.
Yeah. So I guess whoever's remaining here, kind of on the interested in talking about technical stuff, and I'm interested in technical stuff too, even though I've not programmed, stopped programming for a long time. But this is the fun stuff in ESIP. Any other points that? By the way, Joseph, I intend to attend the Enviro Sensing cluster call later. So we can discuss even more there.
That's great. Scotty Strachan connected with Martha and myself recently about the opportunities and what we are looking to do between the Enviro Sensing cluster and this cluster, and it's awesome. I'm really excited about it.
Yeah, because we actually I don't know if Scotty mentioned to you, but so that I did consider things like sensor ML and how can we utilize the schemas that are already in sensor ML. They're of course tied to the OGC observations and data model, and that kind of thing. So that went through my head earlier, and ultimately I landed up not on the sensor ML and O&M, OGC O&M, but I landed instead in the quasi data model called ODM2, observations and data model 2, I think. So that's where I landed up, fortunately or unfortunately. But I think, so again, this is something that you guys in Enviro Sensing probably have a little bit more expertise in. Like do you guys use sensor ML routinely to think about how you should be managing sensor data, or do you use some other schema, that kind of thing?
Right. Yeah, this is it's fun looking at this and kind of ballooning up and seeing where other just information resources kind of fit in, and specific to the sensor cluster, right? You can track an instrument and where it's ever been. So how many fires has that instrument been in, and or how many volcano mapping projects a LiDAR may have been in. Yeah, it's fantastic to get this, just to be able to drill down to such details from the point where you say it must have data.
And in many ways, because I'm not an expert in kind of the schema and things like ODM and sensor ML and all that, but that has already been thought out by somebody else, like you guys. so what I'm saying is that if the schemas are already there, they're all published, and so the way to make use of the schemas is copy the schemas, use that to instantiate a database. In fact, we want the graph database to have the same properties as what the schemas would recommend. And normally in these kinds of schemas, right, like ODM2 or I think sensor ML is the same thing. These kinds of schemas, you already have what's considered the nodes and the properties more or less laid out for you already in the technical specifications. So it's actually a straight copy and paste from the specifications into the database. And then the real trick is to fill out the graph database with actual examples of how you would actually have done it in real life.
I like that vision.
I don't know if you heard the cat, but cat is saying yes.
I think that would be a really useful. How far have you gone? You showed an example of a 2012 bear report from Colorado. How far have you gone down to kind of populating a knowledge graph from that?
Not far. It remains extremely highly experimental, and this was where Joseph was asking. So this is the kind of theoretical knowledge graph, and this was the point that Joseph was asking: how do you link from like a vulnerability civil infrastructure node in a graph database to an actual like an actual shape file in a repository somewhere? But so this diagram here in the poster, no, this is actually very theoretical lesson. I've not even put this into Neo4j. And part of the problem, and Scott Eckenhead is still around. So Scott Eckenhead is with Canadian Ocean and Fisheries. So we have been talking about, a lot of this is handcrafting this stuff, which is painful. So ultimately, there needs to be some easier way other than handcrafting this mess. Yeah, I don't know. So what do you have in mind, Tim?
Well, we get these bear reports, for every big fire, and but we have like vastly different resources on each report, and so there's like aspects where the schema is similar, but then the actual delivered data is like highly variable depending on the resources of the bear team at the time.
Mm-hmm.
But so, and then there's this, like, I'm going to call it like geographic scaling issue, where there's watershed pour point analysis of, where they kind of take the bark map and then their quality control of the bark map's estimate of soil burn severity.
Mm-hmm.
And then they basically apply it to, a lot of watersheds to just do kind of like spreadsheet analysis on change in time of concentration and flood hazard issues. But so they're breaking down the knowledge graph into these geographic packets on the landscape. And so like some of these objects in the graph are going to have some kind of fascinating things I can't really understand exactly how they're going to work out in this graph tape, but I'm looking forward to trying to figure this out.
And here again, for geography, here again we have OGC to our rescue. There's actually a specification, OGC official specification about geometries and whether this thing overlaps with this thing or this thing is contained within this thing and blah blah blah. So the OGC, there's actually a specification that they put out. So I actually, part of this, you see here has geography overlap. It is a mutation of an OGC specification. Michael, want to see if you have any thoughts about how should we progress with this? Should we push down this direction?
Well, I actually work with Tim, so I have a lot of the same concerns. I'm pretty new in this role here. But I think that it seems really interesting from a standpoint of being able to graphically understand the database, which is a nice change from relational databases. Mm-hmm. But I mean, it seems useful, certainly, to have this working if the actual instantiation works out, I guess. So I'm excited to see what happens with it, certainly.
And in that regard, if we can instantiate a database, even though it's a prototype, where we have been talking with Scott Eckenhead here on the call is how do you make, so the graph database, if you really look at an actual graph database, it's horrible. I mean, like it's got thousands of relationships, millions, hundreds of thousands of nodes. It's a big spaghetti mess. I mean, like it's the biggest spaghetti mess that you've ever seen, right? You can, but the whole idea behind the query is to take a strand, regardless of how many links there are, how long the strand is, but the idea is to from the whole spaghetti mess, you want to extract a couple of strands and display it to the user. And the discussion that we've been having with Scott Eckenhead, again, this goes back to salmon. So Tim, alert, salmon. So what we were having a discussion with Scott is how do you make that kind of graph visualization appealing enough to people who don't care about graphs? Or I mean, like Tim, for example, you work with many stakeholders who probably don't care what a database is, and they don't care, where the data lives. They just want to see how things are connected. And so showing them the raw spaghetti mess is the biggest mistake you can make, because it's a spaghetti. And so what Scott and Bill and I have been talking about is, can you ease the stakeholders into this spaghetti by showing them kind of just a concept map, a very high level concept map of essential concepts first. But if you click on one of those concepts, it triggers a query to the database, and the database will retrieve a couple of strands of that whole spaghetti mess for the for the stakeholder. And so that's what we've been discussing with Scott and others.
So do you mean like a simplified graph as a user interface, sort of?
Yeah, very much so. And Scott can may want to say something, but the Canadians have been playing around with this a little bit more than we do. We have.
Well, sure. Just a couple of very quick comments. The attraction of the knowledge graph is to deal with the complexity of ecological and environmental systems for me. And if the nodes are information, then it's the links between bits of information that's the knowledge. So the knowledge graph was exciting because exactly how things are connected is what you really want to know in the process of gathering information to make some kind of decision. So we do have this context that there's no point doing this unless it's useful to end users who are not programmers, and it has to be supporting some kind of decision or action. Otherwise, it's just making a 700-page wildlife management document that no one's ever going to read. So to get there, we went to building a user interface that was not just user-friendly, but something that the end user community itself could adopt and build with, like a platform. So we used R and Shiny because that's what the marine biologists and statisticians are using. And that's their language. The power users now can add new tools to the UI so that people who are using the knowledge graph can get what they want out of it. But it all comes down to really making things personally valuable for the end user. And that's absolutely right. The free version, mind you, of Neo4j supports 34 billion nodes. But that sounds like a lot, but then of course you've got 100 billion neurons in your brain, so it's competing but not exceeding. To deal with that complexity meant making things personalized, having views of the data that were meaningful to people, and they included, as Brian was saying, perhaps a concept map of what this problem is. In our case, it'd be salmon life cycle. In your case, it might be something like the life cycle of a fire. To say what's important in this situation, what do we need to know? It boils down to this question: who knows what we need to know to make a more fully informed decision? And that's where the knowledge graph let us investigate, discover things that we were not aware of. Who is it that is indirectly connected? And all the indirect connections in the graph are so much more powerful than the merely direct connections in relational databases. Now, I could go on at great length, but I'll spare you. I did put a link up to a talk that I was supposed to have given in Japan, but I actually gave it in my kitchen. That shows the background thinking to what we were doing with knowledge graphs for an environmental problem up here in the Pacific Northwest.
Okay, I will go look at it. It's unusual for a scientific paper to start by saying, once upon a time, long, long ago, in a land far, far away. But I actually did that just because
Part of the whole knowledge graph thing is that there's an element of iconoclasm here. This is a new technology, and it does let us break through some things, but there's a certain amount of breaking required for breakthroughs.
Yes.
That's what I'm having a problem with up at my end.
Well, so the problems that Scott has mentioned. So for those of you who don't know, Bill, myself, and a few others were involved in another small experimental ESIP project on bird conservation. And yeah, there was I don't think the idea of knowledge graphs was very. It wasn't an easy. It was not an easy sell. That's what I'm trying to say. So yeah, we are a bunch of iconoclasts on this call trying to.
Well, but the good news is that we get to help each other. You know, I sent you the code for the R and Shiny user interface. It's simple for you to attach that to your database and then to modify it to be more appropriate. And then we would get back from you your improvements. And so it goes. If we can get more communities involved, we can share this building of a platform together. So I mean, I'm encouraged just meeting you guys and listening to this discussion, like how can we use knowledge graph technology to manage the wealth of detail and the scope of the data and the fact that the data is so dynamic. How can we get a grip on that using a knowledge graph? Listening to that is very encouraging for me dealing with similar concepts up here in Salmon.
Tim, did you have something to say? I mean, we are over time, but we should try to wrap up in the next 6 minutes or so. But
yeah, I was wondering if, well, so we're just about entering, we're well into bear season now in California, at least. But I wonder if like a shared project would be to model out a bear report, you know, and basically get it to an endpoint with Neo4j database out of an existing bear report.
could be, we could try. I have bits and pieces started in a concept map that I can shoot over to you, Tim. The concept map is in the software CMap. Yeah, whatever. I can. We. So are you saying? Oh, Dan is coming in. Dan Foucault. Maybe Dan is here. Hi, Dan. Anyway, but so are you saying? What are you saying? like prototype? Like just instantiate a small little prototype.
Yeah, I mean, basically we have, you know, these, we have like these report models that the Forest Service puts out. You know, they'll put out like probably 30 or 40 bear reports in California this summer. And basically like the demonstration of value would be to, you know, one, make a process that accelerates the capture, or basically facilitates the capture of data from existing kind of data streams that the Forest Service already has working, like like the reporting into InstaWeb or other things, and then basically just like see this, you know, see I guess a reproducible instance of a working Neo4j database for a burned area. You know, like what would it look like just kind of pushing it to a deliverable that would be kind of affect people's work lives who are working in the post-fire environment.
And you know, to that will be helpful if in addition we can identify a proper, I mean not proper, I mean if we can identify a good use for that database, that will, because the intended use, like for example, would it be useful for future fire managers? That was an example I just pulled out of air, but earlier I said, you know, to look at the land stabilization treatments that have been used in the past, and to figure out the relationship between land stabilization and landscape features, like did the fire occur on the south slope or is it the north slope, at how steep of a slope, that kind of properties can be captured. And so if we can figure out that use case, right, of somebody saying like, wow, if I could ask the database this question, that would be useful for me. If we can figure out that question, yeah, then we can drive the shaping of the database to answer the question. Scott?
That was the key thing for us, dealing over 4 years with all the bureaucrats in Fisheries and Oceans Canada, was to try and come up with the question that was really important, really hard to answer with the technologies they have now, but easy to answer if everything had been built into a knowledge graph. What it actually came down to at our end of things was trying to deal with 10,000 salmon restoration projects, all of which dealt with thousands of agencies. And there was no idea of who should be collaborating together and where were people working together that should know each other that didn't. And so we actually ended up tracking down collaboration opportunities as the key question that they couldn't answer now, that we could answer easily. I'm sure there must be a similar question about wildfires and wildfire data management. It's critical, hard with conventional technology, easy once things are glued together in a knowledge graph.
And Tim, I know you focus on wildfires, but I do, the Watershed Center does have conservation projects with multiple partners like TNC and yada, 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 right, all over the place, which would fit a lot into the scenario that Scott had just described, where you have multiple partners working in the same landscape, actually on the Pacific West Coast, I mean, on the Pacific Northwest too, as it so happens. So yeah, knowledge graphs are great for that.
And that is a phenomenal observation Scott made, as like identifying partners that don't know each other as being a huge need.
For sure,
I feel like the partnership coordination is like stolen the data science part out of my job, because it's just like, coordinating between different organizations that are kind of have different constituencies is huge. But like in this case where we're talking about the burned area emergency response, it is easy for there to be no decision made in the current circumstances if people don't recognize that there's like choices being made about whether or not these funding requests are being completed. So like, I think a lot of agencies don't even understand when they're making choices, when they're just overtaxed and they're kind of, they're just playing triage. And a lot of times, the bear reports should be informing like this huge network of options where there's limited amounts of funds to do a very limited amount of treatments to the watersheds. And, but I've seen in the last year where the agencies are so overworked, they just don't even get to make, a rational decision about resource investments, much less an optimal decision.
So that could be a tempting question, a tempting legitimate use case, if we were to approach an agency person and to say, if making a decision is part of your job, part of your routine job, and there are going to be more decisions to be made next year when the next fire season rolls around, what if there were a database here that could help you? I'm just saying. But so we are running we're running an hour and a half. But Tim, feel free to contact me, Bill, and we can hook you up to anybody else here on the call if you want to push forth with that idea. Because I can like if you guys want to, like Tim, if you want to pull a small group together and work on this, I can contribute to that group, just as Bill and I are contributing to there's an ontology group which is meeting tomorrow, I think. Right, Bill? I think so. Anyway, so Bill and I are working on an ontology group also on wildfire terminology. So we are contributing in many places. So
is that in the ESIP ontology section on the Slack?
Yeah. In fact, the meeting is tomorrow, I think 2 o'clock Eastern time, I think.
Right. It's a semantic harmonization cluster.
Oh yeah, that's right. Ah.
Well, and that's the thing, is that each of these special, each domain science develops their own schema, and it's making these graph databases kind of naturally extract data out of existing schemas seems like would be powerful. Am I incorrect in this?
Say again.
Well, what I was referring to is so there are these standardized bear reports that are pumped out by the agencies, that they have crews that do this for a quarter of their work year. And we have similar domain sciences that are doing kind of similar. They have standardized products, and what we would be trying to represent a standard product that they've been envisioning for professionally for potentially decades, and building a graph database that captures information that can basically what would be the word, to kind of scrape from their existing reporting pattern.
So you brought up a very interesting thing, because the same thing is happening. So Scott has been part of this discussion too with USGS folks, and Bill and I. There, instead of bear reports, we're talking about state wildlife action plans, which there are mandatory sections. It's well structured. You know what are the sections, and it's important because the states, if they don't do that report, they don't get money from the government. I mean, that's it. Same thing with bear. I mean, bear reports. You want to get money? Yeah, okay. You better fill out these bear reports in these sections. So yeah, it's So the way I look at it is, if there is a way to such that when you are creating your bear report, when those bear teams, if you say that they have a vision for a way that they would like to change the way they operate so that they can achieve something that they've been thinking of doing for dozens of years, if that vision for changing the process can involve the creation, the population of some data in the graph database in some transparent manner, meaning that we're not, if you can make it such that we're not asking them to do additional work, right, in order to populate the graph database. But if you're saying that, look, imagine that there's this funny tool, some funny web-based tool that these bear teams use to construct their bear reports. Yeah, they write a bunch of text in it, and that's fine. But there is a way for this tool, as they write their reports, to automatically pull stuff out into the database. That would be great, because in addition, because you can tell the bear teams, right? Okay, you create this tool, you create your reports, and boom, your report is there. You can ask for money, but the additional advantage is that the tool is able to extract data as you write the report out into the graph database, and the USDA is able to say, query the graph database to say, help, I have got 2 hours to make the decision about stabilization treatments. Now, what have those guys out there been doing? And so that's a way for USDA to say, oh, so you wrote a bear report last year talking about this stabilization treatment that's in the database because the database captured that fact alert as you were creating the report. Now, so USDA then would say, oh yeah, that's a great tool to have.
Tim, I was actually wondering, the one part that you didn't expand on, but you did mention, is the part where the different fields or different domains have different semantics for the same, for say the same variables. And what Brian is talking about here, I'm wondering if actually combining these two with the importance of aligning the two different fields and almost aggregating the disjoint semantics for the same. That's the poor way to say it, but could you go further on that and possibly how this might end up in an ideal world where we're actually combining semantics from multiple domains or even multiple labs within the same domain?
In fact, I will show you an example right now where we have begun to do that. Blah blah bear. Is this bear? No, BMC. Sorry, I'm going to share my screen. So what I'm about to show you, Dan, is share screen. It's actually it's an example for the ACC experiment. I haven't gotten too far yet, but what it does is it ingests the ENVO ontology implicitly. Hang on, I'm going to zoom in here. This is a horrible. You got to bear with me. I'm not very good with this interface. I mean, the zooming function is horrible on this thing. Hang on, zoom. Oh boy, zoom too much. Darn it. Sorry. There's this thing. There we go. Oof. Okay. So Dan, in response to your question about semantics, I cannot zoom in. There we go.
Actually, I was going after Tim's initial statement about the multiple domains. With Tim had made the statement and brought it up about the multiple domains and the misaligned. So it's not mine. It's not towards my question. Rather.
Okay.
Well, that was a really that was, I think your question was more insightful than where it started. I'm totally with you that that's important. And you know, like with Scott's work in salmon restoration, we're seeing intersection between fire work and salmon work all the time, and it's getting really fascinating when sometimes our assumptions don't really, you know, our domain assumptions can kind of get mislead us sometimes when we go too widely astray. But you know, I think yeah, this is anytime when you're translating between disciplines, there's going to be challenges, but big opportunities, I think.
So what you see on the screen here, unfortunately, I know some people hate ontologies, and so Scott, I'm not saying that you hate ontologies, but I'm doing a wink about Mark Schutthauer. So there are folks within our orbits who do nothing but ontologies, and you know, I cannot speak their language, so I like to try to incorporate their works, right? So this is a quick attempt to a small little attempt to experiment with ontologies in a graph database. So here what we have is part of an ontology that I grabbed from ENVO, the ENVO that is maintained by, it's a well-maintained interoperable ontology, as in this ENVO ontology on environmental science interoperates with chemistry ontologies. So when I talk about atmospheric chemistry and atmospheric processes, the terms that you define in these different disciplines are traceable. I mean, in the places where there's a relationship. So that it's this fantastic family of interoperable ontologies. Very nice. It's called OBO Foundry, the Open Biological Ontology. I can't remember what it's called, but OBO Foundry. Anyway, so the OBO Foundry, which has many ontologies. One of the ontology is ENVO, and it has this term atmospheric water vapor, right? Atmospheric water vapor, in that ontology, is a more specific concept of something called a gaseous environmental variable. And here I have another example of volatile organic compound is also a instance of a gaseous environmental variable. And so this is a small example only, but you can imagine these terms from different disciplines from within the interoperable family of ontologies being explicitly encoded into a graph. And so when somebody says this sensor, and the reason why this atmospheric water vapor is appearing in this graph is, this is we started to model the San Francisco Bay Area environmental sensors, the one that triggers a cell acquisition. So apparently the sensors measure atmospheric water vapor, which is why we started with this. Anyway, so this is a little small experiment and at some level of disciplinary interoperability. We don't know if this will work. Again, like Scott said, we're a bunch of iconoclasts here, and we're fooling around with this. We're not sure if this will work. But if you were to ask the Neo4j knowledge management people, they will tell you, there's this one guy in particular whom Bill and I we've had conversations with him. His name is Jesus from Neo4j. So this Jesus engineer guy is very smart, and he will tell you that Jesus will import, like actually he demoed it to this cluster, Ag and Climate cluster in a demo we just recorded. Jesus imported these ontologies into his graph and made his graph reason through these imported ontologies. And so that's a way that you can at least get some disciplinary interoperability in there. Again, I'm not an expert at Neo4j, but it's possible. I'm just saying, if somebody knows how to do it, I don't really know how to do it. So there, yeah, this is a bad graph, but at least this part of the graph is the interoperability part there, well, at least the ontology part of it. So yeah, Tim, if you, yeah, that's we should see if we want to find some time somewhere, I don't know where, to talk about the whole bear thing.
Yeah, we have, well, I should just say that, so not where I live, but our main office at the Watershed Center, it's basically right across the street from an evacuation zone. Oh. And like the fire's been, we've got a 187,000 acre fire breathing down the neck of the most of the staff. So we're going to be working on this over the next couple of weeks, that's for sure. Or, a related topic. But so I have a bunch of old bear reports, and I would be, I don't know, I would consider moving down, and try to make one that was, replicable to the bear reports that are coming out in the next couple of weeks.
Hey, Tim, do you have time later this week to follow up on this?
Yeah. How's your Friday afternoon? Noonish? Friday,
Yeah.
Pacific?
Yeah, afternoon is good for me.
Your East Coast time?
Mm-hmm. Yes.
Could it be 3 your time?
Yeah, that works.
Okay.
What about you, Brian?
Oh, I have that speaking up training thingy from 2 to 5 Eastern time.
Oh, okay. I'm doing that in the morning.
Oh, is there a morning thingy?
Yeah, 9 o'clock, 9 to 12 is another session.
Okay, I'll ask to switch. In that case, yeah, that time is free for me too. And if anybody else on the call wants to join us, anyway, I will send out the coordinates later to everybody here on the call. Except Michael, I don't have your email address, but I guess I'll send it to Tim, and then Tim can forward it.
Yeah, mine's just Michael at the same domain as Tim.
Oh,
so,
okay.
Yeah.
Easy enough. Done.
Okay. Awesome. I have to get going, but this has been really informative. I'm really intrigued by these graph databases.
Okay. And so is Dan apparently. Okay, so I will send out the link to everybody. Join us if you can, but remind me again, it's 12 p.m. Pacific time, is that right? And 3 p.m. Eastern. What time is it?
3 Eastern, 9,
Eastern, okay.
or I mean noon Pacific. Is
Okay, got it.
that good?
Yeah, goody. Okay, I guess so. We'll see everybody sometime soon.
Okay,
Thank you.
Hi, everyone.
thanks,
This is
everybody.
Pretty interesting.
all.
Yeah.
Thank you.
Bye.
Bye.